Start this up here. Okay, are we ready or what? So everyone has a handout from last day and a formula sheet, hopefully. If not, you can come grab one here. So assignment 3 is due tonight. Tonight at basically midnight, 11:59. Otherwise it's like tomorrow. No, it gets confusing. So you've probably seen it, the late passes on in the assignments. And so the late passes, Steve was saying that you have to, so also who showed me how this works. He said that you have to apply the late pass before it's due, but it gives you a 24-hour extension and you get 2 late passes for the term. So, so a late pass must be applied before an assignment is due, but gives you a 24-hour extension. Because we all know that sometimes things happen. So, and I think it's a pretty fun thing. It's like you control your own destiny type of situation. So I like that. And so you get 2 late passes in total. And I'm pretty sure you're allowed to put 2 late passes on the same assignment. Don't think you want to do that. Might need it later. But it's that whole, do I spend it right away or do I spend it later? Do I say, and anyways, leaving that dilemma to you guys. But yeah, so those are the late passes. And so let me know if you have any questions. But like I said, it's new to me too, so I'll ask Steve. You ask me and I'll ask Steve. How about that? Okay. How about a little review? We finished up multiple regression, but also the main event was we got into probability, right? Chapter 5 in probability. Chapter 5, which is probability. And as kind of a recap, what I want to do is I want that dang formula sheet. Sorry. Dang formula sheet. I thought I brought it in earlier. I did too. 2019, 2020, yeah. Because what we did, there it is. We kind of took off a whole chunk of this general probability section. And so I'm just going to steal it from the formula sheet. And then we can talk about it as a way of reviewing. So from the formula sheet, oops. Everything that we talked about last day is on here. Sometimes it's a little bit hidden. But we got as far as kind of to here. But also we talked about independent events. So we said, okay, well, just as a rule, probabilities have to be between 0 and 1, right? And so we use that probability notation, P of A, where A is just any event with some probability, right? And so probability of A, whatever A is, it doesn't matter, has to be between 0 and 1. Sum of all the possible probabilities has to total 1, right? If you're talking about all the possible things that can happen, right? The probability of all those things or one of those things happening has to be 1, right? And so if we add up all our probabilities, it has to sum to 1. And from there, we started talking about probability distributions, right? And said that, okay, for a probability distribution to be valid, well, a probability distribution is when we have all the possible outcomes listed, right, in the columns of our table, because a probability distribution is a table. And then below each of those outcomes, we have each of the probabilities, right? And so first thing we had to check was, do we have disjoint outcomes, right? So all these events that we're talking about have to be disjoint, meaning there's no overlap in those probabilities, right? That was the first thing we had to check. Then we had to go through and we had to make sure that each of these probabilities were between 0 and 1, right? No probabilities larger than 1, no probabilities that are negative, right, less than 0. And then we had to make sure that they all sum to 1, right? And that's a valid probability distribution. Then we started talking about, well, a lot of these things we already know, right? Things like the complement of an event. Oh, hard to say. Complement of an event. So the complement of an event is the opposite of it happening, right? And so, and we know the complement, we understand the complement. And I think I gave the example of, oh, there's a 10% chance that we'll end class early today. Oh, because you already know what the probability of the complement is, right? It's got to be 90% that we don't end early, right? And so the complement of the event is just the opposite of that thing happening, right? And it also has a probability, but the probability is just going to be 1 minus the probability that it does happen. And then we talked about, okay, well, if we want to find the probability of A or B, so now we're talking about two events, A and B, right? And so if we want to find the probability of A or B, what we can do is we can think about the probability of A on its own plus the probability of B on its own. But then remember we talked about the cards, we looked at the deck of cards, right? And we had face cards and then we had diamonds, but there's also face cards that are diamonds, right? And so they're not disjoint events, meaning that they share some probability of A and B. And so what we say is, well, for the probability of A or B, face cards or diamonds, I do the probability of face cards plus the probability of diamonds, and then I subtract the overlap to kind of smooth it out a little bit, is how I kind of think about it. Right, because we've counted that overlap twice. And so we also said, right, if A and B are disjoint, then the probability of them happening is together is 0, right? And so we can just always start from the addition rule. This is the general addition rule, it's called, but this is the only one we'll use. So if A and B are disjoint, oops. The probability, I should give myself more room here. The probability of A and B is 0. And we're going to use that fact in the example that we're about to do, right? Because one of the questions is going to be, well, are these two things disjoint? Rather than arguing, yeah, they can happen together, or no, they can never happen together, right? If I have the probability of A and B, if it equals something, then they're not disjoint, right? And if it equals 0, then they are disjoint. And then we establish the rule that, and this thing is only true if A and B are independent. So we use this rule more to check for independence rather than to calculate the probability of A and B. Okay. So we use this to check for independence, not to calculate the probability of A and B. So what we're going to do is we are going to talk about the rest of these formulas today. They look a little bit nastier, right? But it's going to be okay. But first, let's do some examples just as a refresher, because we didn't actually get to the examples last day. And I'll steal this cute little image. And you've got it on your handout, so. I guess that's kind of the end of the review. Start fresh with an example. Any questions though before we do? Oh. Okay. So in a math class of 30 students, 17 are boys and 13 are girls. On a unit test, 4 boys and 5 girls made an A grade, so they got an A on some sort of test. If a student is chosen at random from the class, what's the probability of choosing a girl, choosing an A student? Right. And then instead of drawing a Venn diagram, are you guys familiar with Venn diagrams? You know, have a circle, there's some overlap. Okay. We can draw Venn diagrams. Usually we draw them like this. I'm actually going to suggest that we pulling a girl, maybe it's an A student. Here, this overlap would represent the girl and an A student. Everything on the outside, those are all the boys who didn't get A's. Right? All the girls are in the circle. All the A students are in the circle. There's a little bit of overlap, right? Because there were girls that got A's. Everyone outside, those are boys that didn't get A's. Right? So you can draw a Venn diagram. I think it might be more helpful if we have a look at the two-way table, right? The contingency tables that we've seen before. And so instead, well, let's talk about part 1. Let's figure out what the probability of choosing a girl is, choosing an A student, right? If we have a class of 30 students and 13 are girls, we're just picking at random. Then if we let, and I already used it, let G be selecting a girl, and A be selecting an A student, usually we just kind of use the most obvious notation, right? We don't use A and B anymore because it can be hard to figure out which one's which, right? Here we've got an A, but it's because it's an A grade. I guess not an A student, but I think we know what we mean, right? So we can pull a girl, we can pull an A student, We can pull a girl that is an A student, right? And we know all these probabilities just from these counts that we have. So if we have a class of 30, the probability of pulling a girl, if there are 13 girls, is just going to be 13 out of 30. The probability of pulling an A student, so now regardless of gender, we've got 4 boys and 5 girls that got an A, right? So a total of 9 students out of 30 got an A. 9 out of 30. And I'm just going to leave it exact, right? Later on, we might convert to decimals, right? But it's always nice to have exact answers. Sometimes it's a little bit easier to deal with, actually. Even though we like decimals, right? So it's okay, but I'm gonna leave it exact for now. There's no reason behind it, I just prefer exact answers. So, okay. Instead of drawing a Venn diagram, I was about to say draw. It's not so much drawing as constructing. Construct the contingency table of the outcomes. So it doesn't matter which one you put in the rows and in the columns here, but I'm going to put maybe gender up here and the grade up here. For the gender, it's either a girl or a boy. I'm assuming it's a younger class. I wouldn't call you girls and boys. What's a boy? A boy is essentially the complement of a girl, right? The grade, well, let's just summarize it as either they got an A or they didn't, right? The complement of A. That's easier than saying, oh, they got a B, C, D, whatever, right? We can put our totals on here. So total and total. And we've seen these things before, right? But here they are again. So from this information, right, I know that overall there are 30 students. So no matter what, my total in both the rows and the columns should add to 30. So, and I know in total, there are 13 girls and 17 boys. So down at the bottom here, I've got 13 and 17. We're also told that, what's the other information? So 4 boys and 5 girls got an A. So 4 boys got an A and 5 girls. And then we said the total, right, for all the A students is going to be 9. And we said that the probability of just pulling an A student is 9 out of 30, right? So we can get that information from this table as well. And it's a little bit easier to look at, or at least to wrap your head around. So now, 5 plus blank has to equal 13, right? We know that because these totals have to add up across the columns, but also across the rows. That's how we got the 9 for the total for the A grade. So if we have to have 13 Then 13 minus 5. Eight. So then 4 plus whatever has to equal 17. Nice. So then how many students didn't get an A? Must be 8 plus 13. Math Whiz is in here. And then you just want to double check, right? 9 plus 21 does equal 30, right? So you always want to check to make sure that your totals all work out. Okay, so this is good. Now we can pull all kinds of probabilities from here, right? And so let's have a look at question 3. So what's the probability of choosing a girl who got an A on the test? So if we have to choose a girl who got an A on the test, how can I? I have to choose a girl who got an A on the test, and so that's the 5, right? And so I want the probability of choosing a girl and they got an A, right? If I have to convert it to probability notation, right? So then we have 5 out of 30. In the next section, right, we're going to talk about, okay, well, what's the probability of pulling a girl if I already know I have an A student, right? Because then it's not out of 30 anymore. If I already know that I'm pulling from A students, then I'm just pulling from those 9, right? So then what I'm dividing by is going to be different. For now, we're just talking about the grand totals for a little bit here. Okay? But the probability of choosing a girl who got an A on the test, that's a girl and an A, right? So it's just that overlap. 4 is asking for the probability of G or A. You can look at it and say, okay, well, I either want a girl or an A student, but there's that overlap, right? And so it's actually easier, or I find it's easier to just use the general addition rule because I know the probability of G, I know the probability of A, and I know the overlap, the probability of G and A. So what I'm going to do here is I'm going to say that's the probability of G plus the probability of A minus the probability of G and A. You can do it from the table and you can double check, but I would recommend that you just stick to the formulas as soon as you have enough to use the formula, right? And we talked about, well, we only need 3 of these things to solve for the 4th, right? And it's not necessarily always solving for the probability of G or A. Could be solving for any one of those things. And so the probability of G, we said was, what, 13 out of 30? Plus the probability of A was 9 out of 30 minus the probability of G and A, which is 5 out of 30. What's nice is you're going to have that common denominator, so it's not something that you need to worry about, right? But if you're adding or subtracting fractions, you have to have a common denominator. And so we've got them all over 30, so it's safe, right? And it will be, otherwise you could just convert to decimals and use your decimals, and that's fine too. So now we've got 13 plus 9 minus 5. That puts me at 17 over 30. 13 plus 9 minus 5, 17. So we've got 17 over 30, which if you want to do 17 over 30 on your calculator is roughly 0.566666, right? Or 56.6667. Let's round up percent, right? So we can go between probabilities. Probabilities, remember, are just decimals between 0 and 1, and percentages are when we multiply them by 100. Right? So you want to be really careful. Nice. So if we have all these probabilities, right, then we can use the probability formulas to find other probabilities. Now, I want to know, are choosing a girl and choosing an A student independent? Yeah. So this is one of those situations where we're going to check to see if the probability of G and A, does it equal the probability of G times the probability of A? Because that's how we check if two things are independent, right? Mathematically. We could argue that, because remember, independence is if the probability of one thing doesn't depend on the outcome of another thing, right? And so it doesn't depend on what happened previously. These are just independent events and they're just happening whatever happened before. So we know the probability of G and A is 5 over 30. I almost said 13, that would have been confusing. And I'm just gonna keep doing my equal signs with question marks over it because I'm not sure if they're equal to each other. I never want to say two things are equal when that's not true, right? And the probability of G was 13 over 30. And the probability of A was 9 over 30. So if we do 13 over 30 times 9 over 30, you're just going to use your calculator, I get 13 over 100. Because mine just simplifies things, just magic. 5 over 30, kind of hard to tell, right? So I'm going to convert to decimal places. And so here I get, keep my question mark on there, 0.135 over 30 is 0.166. Repeating. Now I know that those two are not the same, so I don't need that question mark anymore. And I'll say that they're not equal to each other. Since these two things are not equal to each other, right, we know that pulling a girl or pulling an A student, they're not independent of each other, right? So what does that tell us about the girls? If we're pulling an A student, right, then that's not independent of pulling a girl or a boy, right? We don't really know which way it's going, right? It could be that the girls are writing worse on tests, but in this case, right, the counts are showing it's a little bit higher, right? And so we're saying that they're not independent. Even if the value is really, really close, right? 0.132 2, for example, that's close to 0.13, right? But it's not equal to 0.13. So that's what you want to keep in mind, right? They could be really close, but in order for them to be truly independent, right, they have to be equal to each other. Yeah? So now we argue that since the probability of G and A is not equal to the probability of G times the probability of A, we can conclude that G and A I'm using the shorthand G and A because we already established that G is pulling a girl and A is pulling an A student, so you could use those words, but I'm just going to say that G and A are not independent events. Nice. Any questions about that one? No? How about the next example then? Got split over 2 pages, but here we go. I'll pull them in. And again, you can practice drawing a Venn diagram, but I'm going to say, let's change this to making a two-way table. So construct a two-way table or a contingency table, right? I use those interchangeably. A two-way table instead. And the only reason that I want to stick to the two-way tables is because it's going to serve us a lot better once we get into conditional probabilities, right? So another way that we could have this is I just give you the probabilities, right? And so that's going to be a little bit maybe easier, hopefully easier to deal with, right? But what we're going to do is we're going to construct the two-way table right away. And instead of counts in there now, we're going to have the probabilities. And that's okay. Right? The probabilities all have to add to 1, right, in total. And so we know that about it. And so here we go. On New Year's Eve, the probability of a person having a car accident is 0.09. I don't know. Sure. The probability of a person driving while intoxicated is 0.32. Yikes. And the probability of a person having a car accident while intoxicated is 0.15. Yeah. So we're going to make a two-way table, right? So the two events that we're talking about is having a car accident and driving while intoxicated, right? They don't necessarily happen together all the time, right? Although it seems pretty bad, right? So our two-way table or contingency table, whichever you prefer, again, we list our events, right? One in the rows, one in the columns, and usually they'll just have 2 outcomes, right? We can handle more outcomes, but for us, we're just going to max out at 2 outcomes, right, for each thing. And so let's say here, intoxicated is the first one. And then we'll let accident be the second variable. So can separate these here, like so. And so if we so we need a little bit of notation, right? Because I don't want to write intoxicated and accident every time, right? And so if we let I be driving intoxicated or while intoxicated, and A be having an accident, right? If we let A be, how do they say it? Having a car accident, and I be driving while intoxicated, then we're told that, okay, well, I've only got 2 possible outcomes for each of these, and so I can put totals here on the outside. I either get in an accident or I don't. I either drive while I'm intoxicated or I don't. Each of these are going to have their individual probabilities, right? And then there's going to be the overlapping probabilities. Where are we here? So the probability of a person having a car accident is 0.09. And so that doesn't matter if you are driving while intoxicated or not, it's just the total probability is 0.09. And we said, well, all probabilities have to add to 1, right? So the grand total probability here must be 1. Right? So the probability of not having an accident must be 0.91. I'll check. Almost flubbed it. And so now we're told that the probability of a person driving while intoxicated is 0.32. So that's the overall probability, 0.32. Which means I also know the probability of not driving while intoxicated, right? 1 minus 0.32, and I get 0.68. And then the last probability that we're told is that the probability of a person having a car accident while intoxicated is 0.15. I don't like it. We're going to write it out, but the probabilities are not adding up, are they? Driving intoxicated. I should have stuck to my Venn diagram, shouldn't I? Oh, rats. Dun, 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 dun. What do I do now? Scribble it and forget we ever did it? Okay. I'm not happy about it. Should have checked this. It's like, oh yeah, works out. Great. Cool. Okay. How about that? Oh man. Okay. No harm, no foul. It still works. I don't see why. Anyways. If someone was just coming in, I was going to fill them in. But we had a big disaster on our hands. I think they were leaving. Well, I don't know why this one isn't adding up. I don't know what happened. It should just add up. And obviously on a test or whatever, they're going to add up and they're going to be fine. Because what happens is the probability of A, we said was 0.09. That's still true. I do not see. Oh,
Maybe.
I know what happened, but we won't know what to do with it until the next section. Ooh.
Maybe it's only
Ouch.
0.05.
It is 0.15 because I
Maybe
stole it.
it's 0.05.
No, it is 0.15, but I jumped ahead to conditional probabilities. Oopsies. So just forget it ever happened. Hand waving happening up here. No, just forget it. It's a conditional probability. Okay. But for now, let's just look at the probability of A. Okay. Here, don't do this. And we won't even do that. How about that? List the 3 probabilities given using probability notation. Okay, that one we can do, right? Because we said the probability of A is 0.09. The probability of I is 0.32. And the probability of A and I is the 0.15. Those are the 3 probabilities that we're given. Okay. Fine. I admit defeat. 3. So that's question 2. We're kind of skipping question 1. Are having a car accident and driving while intoxicated disjoint events? Right. So rather than saying, okay, well, here, obviously, they can happen at the same time, so they're not disjoint. But the way we're going to argue it is that because we know that the probability of A and I happening together is 0.15, right, they can't be disjoint. And so since the probability of A and I equals 0.15, which is not equal to 0, we know A and I are not disjoint, right? Because remember, if they're disjoint, then the probability of A and I must be 0. What is the probability of a person driving while intoxicated or having a car accident? So now we want to know the probability of A or I, which we know is the probability of A plus the probability of I minus the overlap of probability of A and I. And that's from the general addition rule. So if we're solving for the probability of A or I, but we know the probability of A is 0.09 plus the probability of I is 0.32 minus the overlap of 0.15, I get 0.09 plus 0.32 minus 0.15, I get 0.26. Yep. Five. Are having a car accident and driving while intoxicated independent events? So now we have to check to see if they are independent events. And so we're going to check to see if the probability of A and I, does it equal to the probability of A times the probability of I? We know the probability of A and I, yeah.
The last question, sum is like answer is 1.07.
No, that can't be. But also make sure that you're doing 0.09 plus 0.32 minus 0.15. Are you doing minus? Are you sure? Good. Zeros make a big difference. The probability of A is 0.09 and the probability of I is 0.32. And so 0.09 times 0.32 is 0.0288, which is not equal to 0.15. Therefore, A and I are not independent events. Whoops. Nice. Let's forget about that example. No, it's a good example, but it's just re-emphasizing what we did earlier. Let's get into conditional probabilities. So as you can see, they're lurking around everywhere here. So what I'll do is I'll just steal from here because it's going to be easier for me to write around it. But section 5.2 is on conditional probability. I'll use my contingency table that works. Overcomplicated things. And so what we're looking at here is a sample of 792 teens, where college means the teen went to college immediately after high school, and the degree variable indicates whether at least one parent of the teenager completed a college degree, right? And so if you're, picking a random teen, right, either they're going to college or they're not going to college. It's simple as that, right? But you could also ask them, hey, did at least one of your parents go to college? Yes or no, right? And so we've got this degree, and then, or actually, not just did they go to college, do they have a degree? But let's assume they're one and the same, even though they're not always the same. So here, right, we've got this degree. And then here we've got the college. So we've got the counts in each of these cells, right? And so from here we can pull a lot of probabilities, right? But what we want to get into talking about now is the conditional probabilities that we kind of touched on earlier, unintentionally. Is, well, what's the probability of a teen going to college given that their parent has a degree, or at least one of their parents has a degree? So now we're chiseling down our sample size, so we're not talking about all 792 now, right? We're talking about all of those teens whose parents, one of them at least, has a degree, right? And so now we're talking about the total of 280 instead of the 792. And so again, we developed some notation, and usually it's easiest if we just have, at least one parent has a degree or not, right? The complement. So we've got D and then the complement of D, and then we've got C, which is the kids going to college, or the complement of C, which is just the kids not going to college, whatever. Okay, and so we'll develop this through an example. So we can talk about all these probabilities. Wait. So what proportion of teens, maybe I'll make room here. Wait. What proportion of teens have at least one parent with a college degree? So that's the same as the P of D. And let me see if I've got, no, I don't think so. This is asking for, just in general, what's the probability or what proportion of teens have at least one parent with a college degree? And so that's going to be the 280 out of 792. Wait. Yeah, but with the parents, right? Yeah, because it's asking for, so at least one parent with a college degree, which is what we're calling D. So given that at least one parent completed a college degree, right? So now we're only talking about out of those 280, right? Because we know that we're pulling from that group. What's the probability that the teen went to college right after high school? And so what we say is that, well, the probability of C given D, and we'll have better notation for that in just a second here. That's going to be the 231, right? Those are the kids who went to college out of 280 whose parents have a college degree. 231 out of 280. The probability of C given D, we can write as the probability of C, and then a vertical bar says given D. Because you don't want to be writing out a bunch of words. It's fine if you do, right? If you prefer to write out given, that's fine. But you have to be able to read that vertical bar as given, right? Because that's how I'm going to write it. And if you choose to write out the word, then that's fine, right? But it's important that you're able to read it and know what it means. Right? So now, the third one, the third probability, given that a teen is randomly selected and she did not attend college right after high school. Okay, so now we know that we're pulling from everyone who didn't go to college right away. So that's 347. Okay. What's the probability that at least one of the parents has a college degree? So out of those 347, 49 of them have a parent, or at least one parent who has a college degree. And so if we have to use notation for this, this is the probability of at least one of the parents having a degree, given that they did not go to college right away, right? The complement of C. Because we're told that, okay, now the people that you're going to focus on are those who didn't go to college right away, right? And then what's the probability of at least one of the parents not having a college degree? I think it's like construction. I think they're working on like the bathroom or something in there. I don't know. Weird. It's like this faint, like, I'm sure y'all hear it. Anyways. Right, if we want to pull this probability now, remember the total is out of the 347 and the ones with degrees is 49 out of 347. Let's see here. So, steal all these notes here into today's notes. What we're gonna do is we're gonna define the probability of A given B, right? The probability of A, and then we've got this given B. So knowing that B has already happened, what's the probability that A is gonna happen? So just on your formula sheet, you've got the probability of A and B over the probability of B. And so it's not something that you have to memorize because it's on your formula sheet. Right. In fact, both of these are on your formula sheet. The first one, oh, pull it from here. Whee. But notice that we can rearrange this, right? We can say that, okay, well, if I know that the probability of A given B is the probability of A and B over the probability of B, if I want the probability of A and B, right, I can just move the probability of A. I can multiply both sides by the probability of B. That didn't make sense. The probability of A given B, make it more obvious, times the probability of B is the probability of A and B. And this I guess it's this one, but it doesn't actually matter, is how we're going to find the probability of A and B for conditional events, right? But the thing is, if A and B are independent, then the probability of A given B, well, the probability of A doesn't care if B has happened or not, right? And so then the probability of A given B is just the probability of A. So what we'll say is if A and B are independent, the probability of A given B is just the probability of A. Right? Since the outcome of A does not depend on B. Question?
I was wondering how that would be. So, the example is D given like C to little c.
Mm-hmm. So then it's okay, right, if we've got the table. It's a little bit harder if we don't have the table, but we'll always have the table for these problems, right? And so then you would look and see which ones satisfy the criteria and just pull that guy. Yeah. So because what we're doing, right, is the probability of D given not C, well, that's the probability of D and not C. Right? So D and not C over the probability of, what were we given? Not C. 347. Those aren't really probabilities, but it still works out because things cancel. So I cheated a little bit. But they have the same relationship. So we're allowed to do that. But usually we have probabilities. Okay. What else did we want to talk about in here? Wait. Oh yeah, just some notation. And it all got smushed in here, but marginal probabilities are the probabilities in the totals, right? The total probabilities. So on the outside in the margins, right? And then the joint probabilities, they're all the joint probabilities in the body of the contingency table. And so up here, these would be marginal totals. See? And these are the joint totals, which would later make up our joint probabilities and marginal probabilities. And I'm pretty sure, yeah, I didn't need to draw it on that one. I've got the probability distribution on the next page. So we've converted all these counts to probabilities, and you can just double check to make sure that all those totals work out. Everything's hunky-dory here. Now these are all probabilities. And so again, now these are marginal probabilities. And these guys are joint probabilities. Oh. What other things did we define here? Yeah, it's good. So here, right, and I think it's in your notes, pretty sure. One thing that I do want to highlight, it's in there, but sometimes it's hard to see. So if we're just using the raw counts versus using the probabilities, we are going to get slightly different answers just because of rounding, right? If you're rounding your probabilities, you're going to get slightly different answers. And of course, on the test, I'll only give you one of these, and so I'll know which one to expect. But even if I gave you the raw counts and you converted it to the probabilities, where you're probably having to round some of these probabilities in the table, it doesn't matter. I just follow through what your work is, right? And so if your work makes sense, then that's good. So for example, if we have to find the probability of C given D, so that's the probability that someone went to college given that at least one of their parents has a college degree, we would find that count to be 231 over 280, which if we're 231 out of 280, I get 0.825, no more decimal places. Here, if I'm using the probabilities, right, the probability of C and D over the probability of D is how I can rearrange this thing, right? And so the probability of C and D, well, C and D has a probability of 0.29. And then the probability of D has a probability of 0.35, so 0.29 over 0.35. But both that 0.29 and 0.35 have likely been rounded, right? And so even when I use those rounded values, and so here, these are rounded values making up another rounded value, and that's why we're going to have different results, slightly different results. But as long as you show me what you're doing and showing your work, then you're fine. Okay. Last thing we'll get to talk about is a lot of the time we're going to have consecutive events, right? First you write test 1, then you write test 2, then you write test 3, right? What's the probability of getting an A on each of those 3 tests, right? There's individual probabilities, but then there's a probability of getting an A on all 3 in total, right? And so we're not going to go for 3 layers, right? But how we organize this is we're going to use a tree diagram. And so that's the last thing in your notes here. Put it on the next page here. So if we're talking about consecutive events, right? So first this happened, then this happened, then this happened, right? First I roll my die and I roll a 2. Then I roll it again. I roll another 2, right? There's a probability of not rolling a 2 at every step, right? But there's also a probability of rolling a 2 followed by a 2 followed by a 2, for example, right? And so we need to organize that, in the easiest way, like I said, is a tree diagram. And so a tree diagram in general is going to look something like this. And then maybe there's 2 more outcomes. It can get a little out of hand, right? If you imagine having 3 possible outcomes for each of these, it gets a little crazy. And then you add on another layer of 3 possible outcomes each. So each little branch have our tree here. So you want to plan out your space, blah, 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 blah. Gets messy, right? And so what you want to do is you want to think about, okay, well, here, I'm going to call this my first layer. Or the first event, but I like to think of them as layers. And sometimes you'll see tree diagrams on the side. It doesn't matter. Sometimes if you're seeing it in textbooks, it'll be easier to print because it'll be easier to write across the page than down the page. But that's probably the only reason. So for us doing them by hand, right, we're gonna have our first layer of events. So all the possible outcomes for the first thing that happens. Right? Usually we're gonna boil it down to only 2 things can happen at each layer, right? And so here's our first layer. Here's our second layer. And here's our third layer. The reason I say this is because later on when you're asking me questions, I'll probably say the first layer, second layer, there's only going to be 2 layers. So our trees will usually, and I'll warn you if it's going to be bigger, right? But let's just focus on a tree that looks like this. Two possible outcomes. 2 possible outcomes at each. Usually we say trial. No, that doesn't really make sense, but usually we say trial, right? Or layer, if you prefer. Right. In the example, we've got 13% of students earned an A on the midterm. Of those students, 47% got an A on the final. 11% did not get an A on the midterm, but got an A on the final. And so here, right, our first layer is going to be what happened on the midterm, and then our second layer is going to be what happened on the final, right? You can either get an A or not on the midterm, an A or not on the final, but even if you didn't get an A on the midterm, you could still get an A on the final, right? There's no reason to think that that can't happen, right? And so here, our tree diagram is gonna just show us what's going on. I'll use the example. I'm gonna run out of room here. Anyways. First thing I'm gonna do is I'm gonna because I need something to denote an A on the midterm and an A on the final. A's they're not very good, right? Because, well, they both have A's, right? And so what I'm gonna use is I'm gonna use M for an A on the midterm and F, ironically, for an A on the final, right? Something like that. And you can come up with your own kind of notation. As long as you tell me what you're using, right, like I'm doing now, then you're safe. So let M be an A on the midterm. And let F be an A on the final. Okay. So now we're going to think about this tree diagram as consecutive events, right? First thing that happens is the midterm, right? I can either get an A on it or I don't. We move on. Next set of events, right, is the final exam. And so here, bless you, try to give myself enough room. It's always a struggle. I can either get an A on the midterm or I don't. And so let's call this first layer the midterm layer. Or branch, or whatever you want to call it. Everyone writes the final, right? So here at our next trial, right, the final exam, if I got an A on the midterm, I can get an A on the final, right, which I am denoting by an F, which is weird, I know, but can't think of any better notation. Or I don't get an A on the final, right? Even though I got an A on the midterm, it's possible that I don't get an A on the final. And so here, this is the final exam layer. So here are all the possible outcomes that can happen for the final exam. So even if I didn't get an A on the midterm, right, I could still get an A on the final or not. At the end of each of these branches, I'm going to have all the possible outcomes, right? I can either have an A on the midterm and an A on the final, or I can get an A on the midterm and not an A on the final. Right, so I'm just listing these as they trickle down each of the branches. I could not get an A on the midterm, but I could get an A on the final. Or I could not get an A on the midterm and not get an A on the final. So how we read these is A on the midterm and A on the final. Each of these is going to have a probability. And basically what we do is if we're saying and, we're going to multiply those probabilities. So we multiply those probabilities down the branches, but I know I'm out of time. So stay tuned, cliffhanger. Any questions before we stop? No? Give it a try. At least putting out those probabilities, but that's where we'll start next day. How about? See ya. Let me check.